Topic 3.10 is about solving trigonometric equations and inequalities. So, like every type of equation we've learned thus far, you can graph them, you can read about their graphs, we know their values, and we can also solve equations with them. So, a question for you to consider: are the following two equation statements equivalent? Is sine of x equal to 1/2 the exact same as inverse sine of 1/2 equal to x? We learned about inverse sine last class. Are those equivalent? Ooh, thank you for answering no to my trick question. Last class I told you that rewriting inverse trig functions means you would just switch the output and the input, which is what I did here. The problem is, we know that around the unit circle, not thinking about the quadrants that I told you inverse trig does not belong, there are multiple places where sine of x could equal 1/2. Sine of x could equal 1/2 at pi over 6. Look at this value right here. This is pi over 6, right? It could also equal 1/2 at 5 pi over 6. So we have these two values around the unit circle where sine of x could be equal to 1/2. So we're not doing inverse trig today, we're just thinking about solving these trig functions, which means there are many different ways that we can write solutions to trig functions. These solutions that we're going to be writing today are called general solutions. I would highlight this word right here. General solutions, or all solutions to a trig function. We have to take into account that we can do multiple rotations around the unit circle over and over again, since the domain of trig functions is all real numbers, meaning that we can meet back up at that coterminal angle like thousands of times. It would take forever, our entire life, to actually write down all of the values of sine that would be equal to 1/2, because we'd loop around the unit circle, then we'd go again and again and again and again. So instead we write a general solution for these things. Here's how we think about it. Again, we know that sine of x is equal to 1/2 at pi over 6, and in quadrant 2 at 5 pi over 6. But since we can make those rotations of 2 pi all the way around the unit circle and land back at the same angle, we know that we can also have 13 pi over 6, which is a whole loop beyond pi over 6, or 17 pi over 6, which is a whole loop beyond 5 pi over 6. And we can keep doing this over and over and over again. So instead, we write the general solution. For sine, we would write the general solution for sine of x equal to 1/2 as x equal to pi over 6. That's the first time sine is equal to 1/2. Plus 2 pi k, which means rotations around the unit circle. Now again today, like last time, I do need you to say where k is an integer over and over again for your problems, unless in the question itself or in the directions it says k is an integer. Keep that in mind. The second time that sine of x is equal to 1/2 would be at the angle of 5 pi over 6. And then also every revolution beyond that. So our general solutions here for sine of x equal to 1/2 are going to be both this general solution and this general solution. So we have two solutions to this function that we're writing that are general equations that allow us to loop around the unit circle many, many times. It allows us to write the infinitely many solutions very quickly without having to list them all out. If we think about cosine of x equal to 1/2, thinking about your unit circle, when is the first angle that cosine of x is equal to 1/2? Pi over 3. And then we can include every coterminal rotation of pi over 3. So we say x is equal to pi over 3 plus 2 pi k, where k is an integer. What angle is the second time cosine is going to be equal to 1/2? Let me rephrase. What other quadrant is cosine going to be positive in? The first, well, this is the first one. What other quadrant? The fourth one. So the pi over 3 version in the fourth quadrant is 5 pi over 3. But every coterminal rotation around the unit circle is also going to return a solution to this equation. So we say x would also be equal to 5 pi over 3 plus 2 pi k, where k is an integer. The 2 pi k means rotations around the unit circle. So you find the two values for sine and cosine where it's equal to that number, and then you tell me that it's also all of the rotations around the unit circle. Tangent is a bit different. So because tangent does not have a period of 2 pi, we don't answer the same for tangent. For tangent of x equal to 1, the first time tangent of x is equal to 1 is at pi over 4. Do you agree? The next time it's equal to 1 is a 180 degree rotation into quadrant 3, which is a pi rotation into quadrant 3. We don't have to write two solutions for this one because saying pi over 4 plus pi times k is all of the rotations around the half unit circle, getting us into quadrant 1 and quadrant 3 over and over again. That's where tangent is positive. Now this again is not really going to make sense till we just start doing some of the solving. So let's try one before we ask any questions. We're going to find all of the solutions to the equation cosine of x equal to negative square root 2 over 2. So thinking about your unit circle, we write the following. I like to show my work like this. Cosine of what is going to be equal to square root 2 over 2? I said the positive one on purpose. Positive square root 2 over 2. Pi over 4, but we know we're going negative. So what's the first quadrant where it's going to be negative? Quadrant 2. The version of pi over 4 in quadrant 2 is 3 pi over 4. Now there's another place around my unit circle that this is going to occur. Where is the other quadrant where cosine would be negative? Quadrant 3. What is the version of pi over 4 in quadrant 3? 5. Because it's 1 more than 4 over 4. So we know from this that the two places that cosine of x is going to be equal to negative root 2 over 2 is at 3 pi over 4 and at 5 pi over 4. And if I were only asking for the first rotation numbers, this would be the answer, but I wanted all of the solutions. So the way you answer this question is you say x would be equal to 3 pi over 4 plus 2 pi times k, where k is an integer. And I'm going to use a shorthand for this. You're allowed to use it for me. I will tune up to know if it's allowed on the AP exam. I assume that it is. There's a symbol for is an integer. You would put this, which means is an element of, and then the symbol for integers is a bold Z. You're allowed to use this shortcut for me. So that's just saying where k is an element of the integers. It's set notation for this. The second answer to this would be x equal to 5 pi over 4. Again, plus every rotation after that, 2 pi k, where k is an integer. This is how you answer this question. So you're not just finding me in one rotation or revolution around the circle what the solutions are. You're including all of the ones every rotation after that. Can we try another one? So knowing this unit circle, I've said this for feels like months now. We have to know these values around the unit circle. In example 2, it says find all solutions. That's the hint that I want that general equation. Find all solutions to the equation sine of x equal to negative 1. So think about your unit circle. For sine of x, what is the value that would get me negative 1? That is a vertical distance of negative 1. 3 pi over 2. So if I know that 3 pi over 2 is a place where I get negative 1, are there any other places around the unit circle where the y value will be negative 1? No. So there's not a second equation for this one because there's only one place where sine of x is equal to negative 1. So we take this value here and we include it in our general solution. So our solution here would be x equal to 3 pi over 2 plus what? 2 pi k, where k is an integer. That's the solution. Because it's saying every time we get to 3 pi over 2, sine is equal to -1, and then every rotation that we go around the circle after that returns the same value. Example 3, find all the solutions to the equation tangent of x equal to 1 over square root 3. Now right now y'all will probably all say, I don't recognize that as something from the table or something from my unit circle, because I've made you rationalize all your denominators. What is this actual value if I rationalize that denominator? Square root 3 over 3. That's something that we recognize from our table, yes? Okay. What is the value of x? Like, what number can I put right here to make tangent equal to square root 3 over 3? Pi over 6. So if I know that tangent of pi over 6 is root 3 over 3, tangent is the one where you only have to find one solution in quadrant 1, because we're not going to have 2 places every 2 pi. We're going to have 2 places every pi. Which means I go right here and I take this number and I include it in my general solution. But for tangent, it is not a rotation of 2 pi that starts to repeat my values. Tangent has a period of pi, so we just say pi over 6 plus pi times k, where k is an integer. So 2 things on tangent. Again, it does not have 2 pi in the general solution because the period of tangent is just pi. And it's only going to have 1 equation every time, while sine and cosine could have 1 or 2 equations every time. But of course, these problems have been really simple because I've just been basically asking you to think about the unit circle and return some values to me. What if we make it a little bit more challenging? What if we have a question that looks like what you see in example 4? What's different about this one compared to what we were asking before? It is not isolated for the trig value. So it's going to be a little bit more challenging than ones we did before, but straight up all you need is some algebra skills. Step number 1 in these problems to solve a trigonometric equation is you are going to isolate the trig function, the way you isolate x, the way you would isolate a logarithm, the way you would isolate an x squared. You're isolating the trig function itself. Then you're going to find the corresponding angle measure, which is what we did in examples 1, 2, and 3. Think about your unit circle and find the angle measure that satisfies the equation. Number 3 says to consider any domain restrictions. And I'm not talking about inverse trig here. I'm talking about the problem specifically giving you domain restrictions. So that's problem to problem, not in general, not the quadrants I had you work in last time with our inverse trig functions, just domain restrictions on the problem. And then we'll write our solutions and or general solutions. Okay, so I want you right now, give this number 3 like a highlight for a second, because I want you to understand when I'm asking for this particular part. Because it's not going to happen every time. It's just particular times the way the questions are asked that we'll need to do this. Example 4 says, what are all the values of theta, where 6 times sine of theta is equal to 3 square root of 2? Okay, let's take our equation. 6 sine of theta equal to 3 square root of 2, and let's isolate the sine of theta. I'm isolating the trig function, meaning I want this all the way by itself on its side of an equation. So what am I going to do? Divide by 6. So if I divide both sides by 6, I end up with 3 square root of 2 divided by 6 on the right-hand side. What do you notice about that number? 3 square root of 2 over 6. What can I do? 3 over 6 reduces, right? What does that reduce to? 1/2. So you're saying this really could be written as square root 2 over 2? Isn't that a value on the unit circle that we recognize? A hint, they always should be values we recognize on the unit circle. or else it'd be a calculator question that we're not going to answer today. Okay, so let's think. Back to how we did examples 1, 2, and 3. We have isolated the trig function. Let's find the corresponding angle measure on the unit circle. So again, if I'm trying to put a number right here for sine of something equal to square root 2 over 2, what would I put right there? Pi over 4. But we also know there's another quadrant where the sign is positive. What's the other value of theta where sine would be positive? I think I heard somebody say it. 3 pi over 2. It's in the second quadrant because sine is positive in quadrants 1 and 2. So it would be 3 pi over 4. So these numbers right here are the values that I'm going to write in my general solution. Our general solution here would be theta equal to pi over 4. Yes, I changed it to theta. The variable they used was theta. The variable I use is theta. Plus 2 pi k, given that k, or where k is an element of the integers. How do I write the second general solution here? Where k is an integer. And again, you can write those words out if you don't like the shorthand, but mathematicians make symbols for everything because we don't like writing words out. Boom, those are the symbols mathematicians use. So there we go. That's the general solution for this problem. We did not have any domain restrictions on this problem. So notice there's nothing purple here. Because again, the domain restrictions are going to come from the question itself. But example 5 is going to have some domain restrictions. It says, let f of x equal to 3 plus 2 cosine of x and g of x equal to 2. In the xy plane, so a coordinate plane, what are the x coordinates of the points of intersection of the graph of f and g for 0 less than or equal to theta less than 2 pi? This bit right here, where the question specifically says I'm only caring about thetas between 0 and 2 pi, means that we are not writing a general solution here. We're finding a regular good old-fashioned two-answer solution, not the infinitely many solutions, because I only care about the numbers between 0 and 2 pi. Let's answer the question, though. It says that f and g are going to intersect. What does intersecting mean on a coordinate plane? They're equal to each other. So we're doing, oh, that's not a pen. We're doing f of x equal to g of x. That's what we want to find out when f of x is equal to g of x. F of x is going to be 3 plus 2 times cosine of x, and g of x is just going to be 2. Do y'all see where I got all of that from? From the question, f is defined and g is defined, so I set them equal to each other. So my brain goes, this is a trigonometric equation I need to solve. That first step says to isolate the trig function itself, which means I want to get this cosine of x by itself. Straight up, good old-fashioned algebra, what should I do first? Not minus 2. Minus 3. We're trying to isolate the cosine of x. Remember, guys, when we're isolating, this is just like solving the equation for x that looks like this. If it looked like this, we would subtract 3 and then divide by 2, right? Which means when we, bless you, change that x to a trig function, we're still just doing the same thing. We would first subtract 3 to both sides, which means I have -1. And then divide by the number in front of the thing I'm trying to isolate, so divide by 2. So I'm looking for where cosine of x is equal to -1/2. That is a value from the unit circle we should recognize. What are the two sections, or what are the two angles for cosine that return -1/2? There, why did I write? Boop. 2 pi over 3, because it's going to happen in quadrant 2. And then we know it's related to pi over 3, but we're going to be in quadrant 3. What's the quadrant 3 version of that? 4 pi over 3, so it's 1 more than 3 over 3. Okay. I have these numbers. For this one, again, because of the domain restrictions in purple, I meant to just point. The domain restrictions in purple, I don't need to write a general solution because it only wants the angles between 0 and 2 pi, which are only these two answers. So since the domain restriction keeps me from writing a general solution, you just list out these numbers as 2 pi over 3 and at 4 pi over 3. Because if I added the general solution, it would be going beyond 2 pi, and that's outside of the range or outside of the domain of the problem. Okay, pause for a second. Questions about anything on this page before we go? Okay. So these are simple style equations to solve, but we can also solve trig functions with higher degrees. Degree meaning the power in the problem. So right now, these were all like linear equations because there was only one trig function and it was not squared. But we can also solve trig functions for higher degreed trig values. This is a whole bit here. I'm going to read it because it's a really good explanation of what's happening here. Pardon my reading voice. When we want to square trigonometric functions or raise them to any exponent, we don't want our notation to be overly complicated or ambiguous. So thinking about squaring the variable x, super straightforward. You just write x squared, yes? But if we do trig functions like that, it can cause a bit of an issue. If we wanted to square the expression sine of x, we have to clearly communicate that. If we write this, which would be like just popping a square on the end of sine, that actually looks to me like we're squaring x, then plugging it into sine, which means it's very confusing on what you're intending for me to square. Okay, so instead we must include parentheses around the entire expression and square the outside of the parentheses like this. But again, mathematicians hate writing extraneous things, so we have created a notation that we take that little square and we stick it inside behind the letters for sine, cosine, or tangent. Meaning, if we're doing sine of x squared, we actually write it like this, sine squared of x. This is meaning I'm taking the sine of x value and I'm squaring it. Not squaring the x, I'm squaring the entire sine function. So when you see this, I'm talking about squaring the entire sine function. And same for the higher values. It can be cubed, it can be to the fourth power, and on and on. So when you flip the page, we're going to start solving equations for trig functions that are squared, which means we have to remember some of our quadratic rules since it acts like a quadratic when we're solving. What a nice review for us of quadratics. Example 6 says the function of g is given by g of x equal to 3 minus 4 sine squared of x. What are the zeros of g on the interval from 0 to 2 pi? Two things I want us to recognize out of this question. We have a domain restriction, which means we are not writing a general solution here. We're writing exact solutions. Because I only care about in this problem going one time around the unit circle, not multiple times. Second thing I want you to recognize is that this problem asks you to find the zeros. For a quadratic, for something squared, for any sort of graph, what does it mean to find the zeros? Absolutely, and when we do that, what we do is we set equations equal to 0 and we solve them. So what we're going to do is we're going to take g of x and we're going to set g of x equal to 0. That's finding the zeros. Well, g of x is 3 minus 4 times the sine squared of x. I need to solve this equation. The steps are the same though. I need to isolate the trig expression. I'm going to try to isolate just sine of x, not sine squared of x, just sine of x. I did that highlighting on purpose. First few steps really easy, kind of like the one we just did before. What should I do first? Minus 3 on both sides, I end up with negative 4 sine squared of x equal to negative 3. What next? Divide by negative 4, which means I have sine squared of x equal to 3/4. The negatives cancel out. It's tempting to say we're done isolating, but we actually are not, because that sine is still squared. How do you get rid of something that's squared, though? Square root. So we are going to square root both sides, which means we have plus or minus the square root of 3/4. Whew, sine is isolated. But right now I don't recognize the number that it is equal to as something from the unit circle. So we have to remember what these square roots mean. What can you do with a fraction underneath a square root? Do we know this? We can actually split the square root to the numerator and denominator separately. So it'd be like square root 3 over square root 4. Can we keep simplifying? Yeah, what can we simplify? Square root of 4 is actually what? Do I recognize square root of 3 over 2 as something from my unit circle? Now we're in business. Okay, we start thinking. We need to find the values of sine of x that are equal to positive square root of 3 over 2 and negative square root of 3 over 2. Okay, let's think. Let's start at the very beginning. So if I'm just going with positive root 3 over 2, yes, but there's also one. Here, I'll go ahead and write that one down. Because that's in quadrant 2. There's another one in quadrant 1 that would be equal to the positive version of this. What is it? Just regular pi over 3. All right, great. Really tempting to stop. But don't forget, we had that plus or minus in front of our square root. Which means I also want to know the values of sine that would return to me the negative version of root 3 over 2. What is that one? 4 pi over 3. And what else? Because there's still one more that would give me the negative version of this. 5 pi over 3. Oh my gosh. All of these values would return something that works for this equation. Now luckily, I did not ask you for the general solutions here because we're only working within one revolution of the unit circle, which means you're only answering pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Oh my goodness, indeed. Comments, questions, concerns? Can we try some more examples? At this point, it's just different ways to solve. You've got the trig idea of isolating the trig function and then finding the values for me around the unit circle. It's just going to be a little bit of how do you solve this equation from here on out. In number 7, it says, what are the values of theta between 0 and 2 pi? Oh, look, a domain restriction, which means, am I writing the general solution? No, we're just giving single answers here. Where cosine squared of theta is equal to negative cosine of theta. All right, let's flex our algebra skills here for a second. We need to solve the equation cosine squared of theta equal to negative cosine theta. All right. I noticed that this is quadratic in the idea of it being squared. And when we solve things that were quadratic, we put all of the terms on the same side of the equation to set it equal to 0. So how do I move this to the other side to set it equal to 0? We add it. So now I change this to cosine squared of theta plus cosine of theta equal to 0. Treating this like it's still a quadratic. I know that it's not a quadratic, but it's squared. When we had two terms with a quadratic, maybe something that looked like this. Don't write this down. What did we do with those two terms to continue solving? We did factor. What kind of factoring did we do? That would be for a trinomial. We'll get there. Don't worry. We're not kidding. We'll get there. Guess and check is coming. It's the easier one where we look for things that are in common. The GCF, y'all. With the red equation that I wrote down, what do x squared and x have in common? X. So I would factor it out. So in my question in this problem, what do cosine squared theta and cosine theta have in common? Great. Let's factor one out. If I factor one out, what's left over? Well, cosine squared of theta, if I factor out a cosine, just leaves me with one of those cosines. What happens when I factor out cosine of theta from cosine of theta? It's a great question. It leaves you with a 1. Okay, don't write this down, but just watch. Here's what I just did, because I see everybody with those wide eyes. That means that I just scared you a little bit. What I did is I divided both of these by cosine of theta. This would cancel out the power. These would cancel out to 1. So factoring it out is reducing the degree by 1, or if they're the same number, it becomes 1. Does that look familiar to us? Oh dear. This is what I just did. This is what factoring is. Taking the common things out, it's like reverse distribution, yes? And here's where we all panic. That's okay. Okay, if we think back to how we solved an equation for a quadratic, when I had both terms set equal to 0, all I did was take the first term and set it equal to 0, and take the second term and set it equal to 0. This is the zero product property. Yeah, go ahead. What are the values of cosine of theta that would be equal to 0? Where is cosine equal to 0? Pi over 2. Okay, is there another place cosine would be equal to 0? 3 pi over 2, because that's horizontal distance, so we're moving nowhere on the x-axis at 2 pi over 2 and 3 pi over 2. Now I can't exactly solve the second part just yet because it's not set equal to 0. So I actually have to subtract that 1 to the other side. What are the values of theta that would return to me cosine of theta equal to -1? Horizontal distance being -1. Pi, very good. Again, these are the values that I could stick in there as theta that would be equal to the values that I needed, which means that this number, and this number are my solutions. I don't have to write the general solution because it only wants in this one interval. I am picky enough to want these in number order, which is not necessary. It can be in smallest to largest order or just whatever order you find. Order doesn't matter when it's a list. Let's think back on this question for a second because I lost some people there. First step was to write down the equation. Check, done. I put all of the terms on the same side so that it was equal to 0. Yes? I factored out cosine of theta since they both had a cosine of theta. That's the moment we may need to focus back on when we're looking at this problem. And then I zero product propertied this, which means the first factor is equal to 0 and the second factor is equal to 0. Then they're cute and small and I can solve them. Can we try another one? Absolutely. Thank you for your confidence in me. All right, let's go. Number 8. It says let f of x be equal to 2 sine squared of x and g of x equal to square root 3 sine of x. In the xy plane, what are the x-coordinates of the points at the intersection of the graph of f and g? 4. 0 is less than theta, less than 2 pi. Am I going to write a general solution here? No. No, just regular solutions. We have a domain restriction for the problem. This is a lot like the example from the other page where I'm looking for the intersection, which means I'm looking for what? Where they're what to each other? Equal. Fabulous. So this is f of x equal to g of x. So we plug in the values we have. F of x is 2 sine squared of x, and g of x is square root 3 sine of x. All right, y'all are driving for this problem. We need to solve it. What should I do? Not panic.
Get rid of the square root of 3.
We will eventually do that, maybe. What do we do in this problem first? Sorry, let's look back up here. We want it to be equal to 0. So what am I going to move to the other side here? Yeah, we want to go towards the power just so that that doesn't become negative. It's just easier that way. So I'm going to move the square root 3 sine of x to the other side, which means I'm subtracting it to the other side so that then my equation is set equal to 0. What next? Not cry. What do you notice is in both terms? So what should we do with things that are in both terms? Factor. Wow, we are losing it today, aren't we? So if I factor this out, what's left over? 2 sine of x, good. Minus root 3, yes. That is a successful GCF factoring here. After we have factored it, we set each factor equal to 0 because of the zero product property, which means I have sine of x equal to 0, and I have 2 sine of x minus square root 3 equal to 0. The first bit, easy, because it's isolated already. That trig function is by itself. What are the values of x that would give me 0 for sine? I mean, yes, but no.
Okay, never mind.
What else is the same as 2 pi, though, on the circle? It's 0, which is the same as 2 pi is what you're thinking of. 2 pi is not in our domain for this question, which is why I said yes and no. We can't include 2 pi based on the purple domain. There's another place where sine is equal to 0, though. Where is it? Don't give up. If it's 0, where else is it equal to 0? Pi. Oof. That unit circle, y'all. So I already have 2 of my solutions. I know it's going to be 0 and it's going to be pi. I have to solve this other guy, though. This other one is not isolated for the trig function. I need to get this by itself before I can do anything. Y'all drive. What's next? Yeah, add root 3 to the other side. And then what? Divide by 2. So now I'm asking, what are the values of sine of x that would return square root of 3 over 2? Pi over 3. Is there another one? And 2 pi over 3, because we're in quadrant 1 and 3 for sine to be 1 and 2 for sine to be positive. So since I don't need to write a general solution here, I'm just looking for these values, not the general solution of these values. Again, only because of the purple part of this problem. Otherwise, we'd be writing general solutions. Therefore, we have that x is going to be equal to 0, pi over 3. I can't help myself but put them in number order. 2 pi over 3 and pi. Again, I don't care if they're in order or not from smallest to largest. Technically, a list is a list. I will just put them in number order because I can't help myself. I know we panicked through this. Does anybody want to ask a question before we go on? Yes, go ahead. Yes.
How come on the third line,
Sine.
No, fourth line.
This one.
Yeah, like you just separated it like that.
How come this got, from here to here?
Yeah, like how come that one is also equal to 0 on the right side?
It is. So think about this. When we did quadratics and you maybe solved them and they looked like this, when we were solving for that solution, you'd do the first bit equal to 0 and the second bit equal to 0 and then solve, right? That's the same thing I did here. This is my first parentheses. This is my second parentheses. So both of them, I would set them equal to 0 and solve. Does that answer your question? Okay. All right. Let's take a break from solving these. I'm waiting. No, I waited. Oh, wait, I went back too far. Equations. Let's talk about inequalities for a second. Ooh, deep breath. In Unit 1, whoa, that was like August, we solved inequalities of polynomial and rational functions. Similarly, we can solve inequalities involving trig functions. Grab 3 colors out of the bin for highlighting. I'm going to use green, blue, and red. When we looked at this graph, if I asked you to highlight the sections where the graph is equal to 0, you would put little dots all along the x-axis where this trig function is equal to 0. If I asked you to highlight the sections where the graph is above the x-axis, you'd highlight this hump and then this hump. If I asked you to highlight sections that was below the x-axis, it'd be these two. This is going to help us answer the questions for inequalities, because from a graph, all I have to do is legitimately see what part is above the x-axis and what part is below the x-axis, since this right here is where f of x is equal to 0. So in this example, example 1 for inequalities, it says the graph of f is defined only for negative 2, wow, I just fumbled all those words, negative 2 pi to 2 pi as shown. So we have a domain restriction. We don't have to give any sort of general solution, thank goodness, because it would be wild. It says, what are the values of x for which f of x is less than or equal to 0? Based on the colorings that I did here, what two colors am I asking you to answer with for less than or equal to 0? The what? Red and blue. So we would answer the following. We would say that f of x is less than or equal to 0 on the interval that is negative 2 pi, just that number since it's equal to 0, and then from negative pi to 0, and then from pi to 2 pi. Notice that I included the brackets, the square brackets, because I asked or equal to. If it just said less than, we'd be using parentheses, and we wouldn't have needed this little extra bit right here since the graph does cross the x-axis at negative 2 pi. Do y'all remember doing this way back when? Yeah, okay, cool. We're back to this, maybe. Thank you for your honesty. However, it's not always going to be that simple, because from a graph, really simple. We're just looking above and below the x-axis. But when we're doing this analytically, or as an equation, we must think about the entire unit circle. Gosh, this unit circle, y'all, you're going to get sick of me saying things about it. In example 2, without a graph to show us, my question is, what are the values of theta on the domain restriction of 1 revolution from 0 to 2 pi, for which sine of theta is greater than or equal to square root 2 over 2? Okay, I have provided a unit circle for you on your notes. You have your paper plate unit circle or pictures of the unit circle. I've posted a couple as well. So you're going to want to use this today and eventually be able to do it without looking at a unit circle. But since sine, which I'm asking for, is the vertical displacement from the horizontal axis, we're looking for all the possible angle measures where the y-coordinate is square root 2 over 2 or more. The figure to the right highlights the portion of the unit circle that satisfies this inequality. You can't really see it, but it's right here. This little bit right here is bolded in. If I were to draw a fake horizontal line right here, every y value or sine value across the unit circle that is above that is bigger than square root 2 over 2, because this is the intersection point for point P on the unit circle where the y value is square root 2 over 2. So we would answer this question with that interval from the first angle that causes that to happen to the second angle that causes that to happen. So we would say from pi over 4 to 3 pi over 4. I want my answers in interval notations, but because this is your notes and AP can go back and forth between interval and inequality form, the other way you can write this answer is from pi over 4 less than or equal to theta, which is less than or equal to 3 pi over 4. Those are the exact same. I like interval notation, and you're going to write interval notation for me, but if you read up on the internet and the things that you're looking for that are helping you learn this topic have inequality notation, those are the same things. So again, you're thinking of this unit circle for whether the horizontal or the vertical distance matches the value you need. Yes? Okay. On the next page. Okay. In your notes, like I said, I've given you a nice pretty unit circle. If you would like to use this over and over again, don't write on it so it's not marked up. You also have your paper plate unit circle that we made a few weeks ago, hopefully. Please still have it.
Yes.
Great. Let's answer some more questions though. For example 3, it says let f of x be equal to 4 plus 2 cosine of x, and let g be equal to 3. What are the values of x in the xy plane on this interval, so we're only talking about one revolution. We don't have to write a general solution, for which f of x is less than g of x. All right, let's figure out what values we're actually looking for here. If I'm looking for f of x less than g of x, I just have to replace those equations in those spots. This would be 4 plus 2 cosine of x less than 3. This looks familiar. What should I do to solve this? We're trying to get this by itself. Yeah, so same as an equation, we're going to want to isolate that trig value. So we will subtract 4. I get negative 1. What next? Divide by 2. So I'm looking for where cosine of x is less than negative 1/2. So on my unit circle, I am looking for the values that are the x values, the horizontal displacements that are less than negative 1/2. I notice that I have negative 1/2 as an x value here, and I have negative 1/2 here. Do y'all see those? Okay, I'm going to mark mine up. Again, if you have already lost your paper plate unit circle, don't do this because you need to use this unit circle over and over again. But honestly, these are your notes. Do what you want. Okay, I have this section here. I'm looking at these values for where all of the cosine values are less than that. These are all smaller x values than negative 1/2. They're smaller, right? Smaller numbers. Okay, so that means that the answer to this is the interval here from the angle where it first starts, which is 2 pi over 3, to the angle where that stops, which is 4 pi over 3. Notice that I switched to using parentheses because it's just less than, not less than or equal to. Again, because these are your notes and you may see it written this way, another acceptable answer is 2 pi over 3 less than x, which is less than 4 pi over 3. Both are acceptable. I prefer this one. In number 4, last one for today, right? Yeah. Let h of x be equal to 3 cosine of x and let k of x be equal to square root 3 plus cosine of x. What are all of the values of x in the xy plane? Ooh, restricted domain, so I'm not writing a general solution, for which h of x is greater than k of x. Same idea here. We want the h of x to be greater than k of x. Y'all are driving on this one. So I substitute my values in. And then what?
Subtract radical 3 plus cosine x. Right?
If those were multiplied, yes, but these are added. So for this one, I'm going to want to get all of my trig values to the same side. There's no square here, is kind of what I'm getting at. I want to get all of my trig values to this side and all of my regular numbers to the side by itself, which is always what we're doing. But these had been multiplied before. So I'm actually only going to subtract this bit. So this would end up being 3 hold on, let me back up for a second. Sorry. If I subtract this over here, I have 3 cosines of x minus cosine of x. How many cosines of x do I actually have over there now? 2. Those are like terms. We can actually add them together. Got ahead of myself a bit. Because they're like terms. One's not squared. We couldn't do that earlier because one of them was squared, which is why we didn't. We're almost isolated because we want the cosine of x by itself. What do? Divide by 2. Okay. We need to know where cosine of x is greater than root 3 over 2. So I'm looking for x values of root 3 over 2. So if I go look at my unit circle, I see that that occurs here and here. So I am looking for values that are greater than this. That's going to be on this side. Do we follow? Yes? Now, writing this one's going to be weird because we are not going to say from 11 pi over 6 to pi over 6. That doesn't make sense. 11 pi over 6 is bigger than pi over 6. So we actually have to take a pause right here in the center. And we write 2 intervals because we are going from 0 to 2 pi, not from negative numbers and not jumping around like that. So we would actually say that this is going to occur from 0 to pi over 6. And then again from 11 pi over 6 to 2 pi. So if you're looking at this, again, because I'm going around the unit circle in a normal direction, not negative, because it said I have to go from 0 to 2 pi. If I start at 0, I've highlighted from 0 to pi over 6. No highlight, no highlight, no highlight, no highlight. Highlight from 11 pi over 6 to 2 pi. Using this unit circle is going to be super helpful. Again, you have your paper plate to look at. Hopefully, maybe if you don't, you didn't completely highlight over this where you can't use it. There's also unit circles linked on Google Classroom that you can see as well.